In our last video, we started working with a moral hazard problem, looking at how to design the optimal contract. And in that first video, we looked at an overview of the problem and then solved the problem in the case where we could observe the effort of the agent. In this video, we look at the last part of the problem where we solve for the optimal contract when we can't observe the effort of the agent. I'll put a link to that first video in the description of this video below. Now let's look at the more complicated case where effort is not observable. So this is really where the moral hazard problem comes in, when the principal can't tell whether their employee is providing high effort or low effort. What we're going to have to do here, since we can't observe the effort, we can only observe the output, we're going to want to set up a wage structure where, since effort is correlated but not perfectly related to output, we're going to have to reward this person with a higher wage for higher output, but we can't punish them too much when there's low output, because it might not have been their fault. So we're going to set up potentially two different wages here. We'll call them WH whenever we observe high output, WL when we observe low output. And of course, we're going to want to make the higher wage higher, right? The problem that we're bringing in here is, since this agent has a risk-averse utility function, that square root of W there, we're going to have to compensate the employee for bringing in this uncertainty into their reward structure, especially in cases where we're going to try to induce them to provide higher effort, which is costly to them. Let's set up this expected utility problem for the agent and ask, well, how could we get low effort? What does the set of wages look like? This is step one, that would provide the low level of effort. When they provide a low effort, there's going to be a 1/3 chance that we get that high output. So we'll give them the high wage, right? So there's going to be a 1/3 chance that we pay them the high wage. So square root of WH would be their utility. Plus there's a 2/3 chance they're going to get the low wage. So square root of that for the utility. And that has to be, the set of wages in their expectation has to provide at least a utility of 10. Now remember, this C, the cost of effort, but we're ignoring that here because C is 0 when they're providing the low effort, so we can ignore that here. So that's the first step. What are the set of wage contracts that would guarantee a utility of 10, expected utility of 10 to this employee? Now we need to figure out what's the cheapest way. Now there are a few ways we could go about doing this. We could do a brute force mathematical approach, where we could say, well, what's the expected cost of the wages to the principal? There's a 2/3 chance we're going to pay them the low wage, a 1/3 chance we're going to pay them the high wage, and we want to minimize that. So we could set up a minimization problem where we want to minimize that 2/3 times the low wage plus 1/3 times the high wage, subject to the constraint, and this is going to be the constraint up above. And what we could do there is we could solve this constraint for WH, and let's solve it for equality. So we just want to guarantee they have a minimum level of 10 utils, and we're not going to pay them extra just for no reason. So let's solve it for the equality situation. When I solve that, I get that WH equals 4WL minus 120 square root of WL plus 900. And if we took the derivative after plugging in this expression for WH, and then took the derivative and set it equal to 0, we'd be able to find the minimum there. And if you do that, if you solve this brute force mathematical problem and then substitute back in, we get that the low wage should be equal to high wage, and it should equal $100. The same exact outcome that we got when we wanted low effort in the perfect observability case. Now, on one level, this actually makes sense. If all we want to do is ensure that the agent comes to work for us, but we don't want them to exert any extra effort to provide the high effort, then all we have to do is guarantee them $100. They'll take the job and they'll provide the low effort. So this solution makes sense. But another thing we probably ought to do here to absolutely make sure that it makes sense is let's graph this relationship here. The WH equals 4WL minus 120 square root of WL plus 900. And what we get here is an indifference curve, this green one. So this is the indifference curve for U equals 10 for the agent when they provide low effort. So this just shows all the different ways we could provide. So here's the high wage on the y-axis and the low wage on the x-axis. All the different combinations of low and high wages that would provide 10 utils. For example, one easy point to see on here would be, what if the high wage we offered was 0? Well, we could offer $225 down here for the low wage, and that would provide an expected utility of 10. But here's that point that we solved for, paying $100 in each case. Of course, that's another way that would provide an expected utility of 10. Now, another way to see that this red point is the point that minimizes this is, let's think about this as if we were talking about a production theory problem, and we had two inputs, WL and WH. What if we were to draw an ISO cost? An ISO cost just shows all the points that cost the same amount, and what we want to do is minimize that ISO cost. Now, typically when we draw an ISO cost, the slope of an ISO cost is equal to the negative of the price of the thing on the x-axis divided by the price of the thing on the y-axis. Well, here we're thinking about the price of the thing on the x-axis as being the price of offering $1 for the low wage divided by what's the price of offering $1 for the high wage. Well, since there's a 2/3 chance that we're going to have to pay the low wage, then the low wage costs 2/3. And the price of offering $1 for a high wage, well, there's only a 1/3 chance we're going to have to pay it, so that costs 1/3. So the slope here is going to be 2/3 over 1/3, or -2. And here's what the ISO cost would look like for this particular solution is $300 for the high wage, $150 for the low wage, and let's connect those with a line here. And what we can see is that this ISO cost I just drew is the closest one down here to 0. So that's going to be the one that gives the incentive to provide a low effort, gives the person a utility of 10, and is the cheapest way in this scenario. Kind of cool. Now, usually in this kind of uncertainty framework, instead of calling this an ISO cost and utility curve, an indifference curve, all that kind of stuff, we would call this a state space diagram. But it's kind of familiar if we put everything in terms that we're already familiar with. Cool. Now let's see what changes if we want to get this person to exert some high effort here. What is the set of contracts? What are the set of wages we could offer to give this person at least 10 happiness in the situation when they're providing high effort? Well, here, because they're providing high effort, C is equal to 1, so we can't ignore that. And so their expected utility, there's going to be a 2/3 chance that we're going to pay them the high wage. So the 2/3 chance that their utility will be the square root of the high wage minus 1 for the cost of providing the high effort, plus a 1/3 chance they're going to get the square root of the low wage minus 1 because they have to provide that high effort. Now, since we have 2/3 times 1 and 1/3 times 1, that just gives us 1. So we can rewrite this as 2/3 times the square root of the high wage plus 1/3 times the square root of the low wage greater than or equal to 11. Now we could go through a similar kind of analysis we were talking about before. We could do the minimization problem. Before we do that, let's solve this because that kind of lets you see what we're going to be graphing here. Solve this for the high wage again. And we get that the high wage equals 1/4 times the low wage minus 16.5 times the square root of the low wage plus 272.25. Now, if we graph that indifference curve, we get this blue one. So this blue one is the indifference curve where this person gets their reservation utility of 10, given that they're making high effort. If we do the same kind of isocost sort of idea, or if we solve this minimization problem, we're going to get this solution that the low wage should be equal to the high wage equals 121. Turns out, even though that's what the math says, this is wrong. Why? Well, let's graph that isocost in the diagram here. So in this case, this isocost is going to have an intercept here of about 363, and over here about 181.5, with a slope of a half. Here's the problem with this solution. Even though it minimizes the cost of getting this person to give us high effort, it actually would provide a much higher utility to this person if they provided low effort. How do we know? Well, look, here's the indifference curve, the green one, where they're providing low effort. If we offered to pay them $121 no matter what, there's another indifference curve when the person provides low effort that's going to provide them much, much higher utility than providing high effort. So that can't be the solution. It's not consistent with making this person provide high effort. So even though our simple little math there works out, it actually doesn't work out in practice. What we have to do here is add in a second constraint. And that second constraint isn't just that we provide this person an expected utility of 10. We have to provide this person an expected utility of 10 if they provide high effort, but we have to make sure that the contract we offer them gives them a lower than or equal to utility of 10 if they provide low effort under this contract. All right, so we actually need to have two equations here at the same time. One is the one we wrote down here, but then we need a second equation that is related to the idea that they're providing us low effort here. So we need to guarantee that if they provide us low effort, their utility will be less than or equal to 10. In fact, we kind of want it to be binding, right? Less than 10. So we want it to be that if they provide low effort, there's only a 1/3 chance they get the high wage, plus a 2/3 chance they get the low wage, and we need that to be less than 10. So we have not just this equation, but we have this other constraint to make sure that the high and the low wages provide us with the right incentives. So if we set these two equations equal to each other, we'll get the solution that solves this for equality. Or what we're really doing here is taking this constraint, right, except with a less than or equal to sign, and this constraint, and we're seeing where the two intersect. And that's what we already have a graph of here. And what we're looking for is this point where these two intersect. And if we solve for that mathematically, we're going to get that the high wage should equal 144, and the low wage should be equal to 81, and that this would provide the right incentives to get this person to provide us with high effort. To solve this by hand takes a little bit of doing. I'll set that up and solve that at the end of the video. If you want to stay for that, I'll spend 5 minutes showing you how to set that up and actually solve that. It involves a neat little trick. But if you don't want that, just take it as given that this is the solution. However, in order to make this an inequality, what we would probably want to do is add just a tiny, tiny, tiny bit to this wage that you would get in the high state and subtract just a tiny, tiny bit from this wage that you would get in the low state to ensure that this person doesn't get an equal amount of utility in practice by providing low effort and high effort. Because technically that's what this solution would give. Although we could do some hand waving and assume, well, the person would provide high effort if they're indifferent. In the real world, we're not really going to be that sure. So what this solution tells us is, again, because they're indifferent, right at this point that they would get 10 utils in the case where they provide high effort and 10 utils where they provide low effort. And given the slope of that isocost line, that is going to be the solution that is the minimum cost solution as well. So now let's take the last step. Now that we know the contracts that we would need to set up in order to get this person, in the case of uncertainty where we can't monitor their effort, to give low effort and give high effort, which one's the best one for the principal? Okay, well, we just need to say, well, if we provide that contract for low effort, which remember was the wage is $100 no matter what, let's calculate our profit. So the expected profit is going to be, in the low effort case, is going to be a 1/3 chance that we get that high output minus paying them $100, plus there's going to be a 2/3 chance that we're going to get the low output. We're still going to pay the person $100. So that means there's a 1/3 chance we would get $300 in profit. So our expected profit would be 100. Expected utility of the principal. What if we offered this contract where we're going to pay 144 if we see the high output? We'll pay 81 if we see low output, and we assume the person is going to actually provide us high output. What is our expected profit as the principal? Well, in this case, there's a 2/3 chance we get that high output level minus $144. Plus there's a 1/3 chance we're going to get that low output level, pay the low wage, 170.67 for this part, 6.33 for this second part. Our expected profit will be 177. So the best choice for the principal is to hire the agent, offer him the high wage package, and our expected profit would be 177. So let's just compare real quickly what's going on, discuss, and then I'll show you the math behind solving for that solution. But let's just discuss here. So in the case where we can't observe the effort, we're going to have to pay a higher wage when we observe high output, a lower wage when we observe the low output, and our profit that we expect is $177. Compare that to the case where everything was observable and our expected profit was $179. So we as the principal hiring people, it costs us when we can't observe effort. So if there was a very inexpensive way to observe the effort level, maybe we'd want to go with that instead of coming up with this complicated wage structure. Last thing, let me show you this math because it's actually a little bit interesting trick here that you have to use if you solve this by hand. So if we just set up these two equations that we had before, right? These two right here, and then we set them equal to try to solve them, then we can move everything to one side of the equation, and then we end up with this expression right here. So let's see how we would solve that. So we can use the quadratic equation. Quadratic equation? Wait, wouldn't that mean that this would have to be squared and this would have to be to the first power? Yes, but what we could do is use the quadratic equation to solve for the square root of WL and then square it. So if this is the square root of WL squared, and this is the square root of WL to the first power, by using the quadratic equation, you can get that the roots of this equation for the square root of WL are -9 and -18.6. And when you square them, you get 81 and 345.96. And then it's a process of elimination to figuring out that, well, that 345.96 is so far away from the baseline contracts that we're thinking of here, where uncertainty is going to change the low wage to be a different number from the high wage, but it shouldn't be changing it that much. And then take that 81, plug it back into this equation up here, and then that will tell you what the high wage needs to be in order to guarantee that they have the income necessary to motivate them to provide the high level of effort. So that's going to end our video here. If you have any other questions or any other things that you want me to go through in a little more depth, please let me know. But otherwise, this ends this long video. I hope this has helped you understand how to solve this kind of mechanism design problem. This is Dr. Berkey signing out. I wish you the best of luck with all your studies.